Polynomial division serves three fundamental purposes in mathematics. Understanding these purposes helps us appreciate why this operation is essential across multiple mathematical disciplines. The first purpose is simplifying complex algebraic expressions. When we encounter a rational expression with polynomials in both numerator and denominator, division can reduce it to a much simpler form that is easier to work with. The second purpose is identifying roots and factors of polynomials. By systematically dividing a polynomial by potential factors, we can decompose it into its constituent linear factors, revealing all of its roots. The third purpose is solving polynomial equations. Division techniques, combined with substitution methods, allow us to reduce higher degree equations to simpler forms that can be solved using familiar algebraic methods. These purposes make polynomial division indispensable across multiple mathematical disciplines. In calculus, it enables partial fraction decomposition for integration. In algebra, it facilitates the analysis of rational functions. In engineering, it supports signal processing and control system design. Understanding these fundamental purposes provides the foundation for mastering polynomial division techniques and recognizing when to apply them in mathematical problem solving. Polynomial long division is a generalized version of arithmetic long division that we apply to polynomials. Just as we can divide numbers using long division, we can divide polynomials using the same systematic approach. The format for polynomial long division follows the same structure as arithmetic long division. We place the divisor on the left, the dividend inside the bracket, and write the quotient above the bracket. The polynomial long division process involves four key steps. First, we arrange both the dividend and divisor in descending order of their degrees. Second, we divide the leading term of the dividend by the leading term of the divisor. This gives us the first term of our quotient. Third, we multiply this quotient term by the entire divisor, then subtract the result from the dividend. This eliminates the leading term. Finally, we bring down the next term and repeat the process until we have processed all terms of the dividend. Mathematically, polynomial long division follows the division algorithm. The dividend equals the divisor times the quotient plus the remainder. Here, f of x represents our dividend polynomial, d of x is the divisor, q of x is the quotient we seek, and r of x is the remainder, which has a degree less than the divisor. The key strength of polynomial long division is its versatility. Unlike other methods that may have restrictions, long division works with any polynomial division problem regardless of the degree or form of the polynomials involved. Its systematic approach ensures accuracy and provides a solid foundation for understanding other polynomial division methods. This makes it an essential tool in algebra and higher mathematics. Synthetic division is a streamlined method for dividing polynomials, but it can only be used in specific situations. This technique offers significant efficiency advantages when applicable. Synthetic division can only be used when dividing by a linear binomial of the form x minus k, where k is a constant. This is the fundamental limitation that determines when this method is applicable. The synthetic division setup uses a distinctive L-shaped arrangement. The value k goes on the left, and the polynomial coefficients are arranged horizontally across the top. Synthetic division offers several key efficiency advantages. It works exclusively with coefficients and constants, eliminating the need to write out variable terms and powers. This significantly reduces computational steps and minimizes the potential for algebraic errors. Understanding when to use synthetic division is crucial. Use this method when the divisor is exactly in the form x minus k, when you need quick results, or when working primarily with coefficients. However, avoid synthetic division when the divisor has degree greater than 1, when it's not in the x minus k form, or when dealing with complex polynomial structures. Synthetic division represents a powerful shortcut in polynomial division, offering significant efficiency gains when applicable. However, its utility is strictly limited to linear binomial divisors of the form x minus k. The splitting the term method is a straightforward approach for dividing polynomials by monomials. This method involves breaking down each term of the polynomial and dividing them individually. The process follows three simple steps. First, we split each term of the polynomial. Second, we divide each term by the monomial divisor. Finally, we simplify each resulting fraction. Let's work through an example. We need to divide the polynomial 6x cubed plus 9x squared minus 3x by the monomial 3x. Step 1. We split the polynomial into separate fractions. Each term of the polynomial becomes its own fraction with the monomial 3x as the denominator. Step 2. We divide each term individually. 6x cubed divided by 3x equals 2x squared. 9x squared divided by 3x equals 3x. And 3x divided by 3x equals 1. Step 3. We combine our results. The final answer is 2x squared plus 3x minus 1. The splitting the term method offers several key advantages. It provides a simple and straightforward process, works efficiently when the divisor is a monomial, and reduces complex polynomial division to basic arithmetic operations. It is important to note that this method is most effective when dividing by monomials, which are single terms. For more complex divisors with multiple terms, other methods like long division or synthetic division may be more appropriate. We will demonstrate synthetic division using a specific example. We need to divide the polynomial 5x cubed minus x squared plus 6 by the linear binomial x minus 4. First, we set up the synthetic division table. Since we're dividing by x minus 4, we use positive 4, which is the root of the equation x minus 4 equals 0. We write the coefficients of the polynomial in descending order of powers. The coefficients are 5, -1, 0 for the missing x term, and 6. We place 4 to the left of the vertical line. Step 2, we bring down the first coefficient, which is 5, below the horizontal line. Step 3, we multiply 5 by 4 to get 20, then add this to the next coefficient, -1, giving us 19. Step 4, we continue this process. Multiply 19 by 4 to get 76, add to 0 to get 76. Then multiply 76 by 4 to get 304, add to 6 to get 310. Step 5, we interpret the results. The first three numbers give us the coefficients of the quotient polynomial, 5x squared plus 19x plus 76. The last number, 310, is the remainder. The final answer is 5x squared plus 19x plus 76, with a remainder of 310 over x minus 4. This demonstrates how synthetic division provides an efficient method for dividing polynomials by linear binomials. Polynomial division extends far beyond academic exercises, finding essential applications in physics and computer graphics, where complex mathematical relationships must be simplified and analyzed. In physics, polynomial division helps model the motion of objects through space. When analyzing projectile motion or orbital mechanics, complex rational functions often arise that require division to simplify and solve. For example, when calculating the position of a projectile over time, polynomial division allows physicists to separate the equation into manageable components, making it easier to analyze velocity, acceleration, and trajectory. In computer graphics, polynomial division is crucial for creating smooth curves and surfaces. Bezier curves, which form the foundation of modern graphics software, often involve rational polynomial expressions that require division for proper rendering. When designers create complex 3D models or animation paths, polynomial division helps break down intricate mathematical relationships into simpler components, enabling real-time rendering and precise control over shape and movement. These applications demonstrate the practical importance of polynomial division in solving real-world problems. By mastering this mathematical technique, professionals in physics and computer graphics can tackle complex challenges with greater precision and efficiency. Polynomial division extends far beyond academic mathematics, finding practical applications in economics and engineering. These fields demonstrate the real-world versatility and importance of this mathematical operation. In economics, polynomial division serves as a powerful tool for data modeling and trend prediction. Economists use polynomial functions to represent complex economic relationships and employ division to analyze these models. Consider market demand analysis. When economists model demand curves using polynomial functions, they often need to find marginal relationships by dividing polynomials representing total demand by factors representing market segments. Economic forecasting also relies heavily on polynomial division. When analyzing time series data, economists divide complex polynomial models by simpler trend functions to isolate cyclical patterns and seasonal variations. In engineering disciplines, polynomial division plays an equally crucial role. Control systems engineering extensively uses polynomial division for system stability analysis and controller design. Control systems use transfer functions represented as ratios of polynomials. Engineers perform polynomial division to analyze system behavior, determine stability margins, and design appropriate controllers for optimal performance. Signal processing and circuit design also depend on polynomial division. Engineers use it to analyze filter responses, design digital signal processing algorithms, and optimize circuit performance through frequency domain analysis. These diverse applications across economics and engineering underscore the remarkable versatility of polynomial division. From predicting market trends to designing control systems, this mathematical operation serves as a fundamental tool for solving complex real-world problems. Polynomial division plays a crucial role in two critical areas of modern technology: finance and cryptography. These applications demonstrate the practical importance of this mathematical operation in solving real-world problems. In finance, polynomial division is essential for calculating compound interest rates and determining loan payments. Financial institutions use polynomial equations to model complex interest calculations, where division helps isolate specific variables like payment amounts or interest rates. In cryptography, polynomial division is fundamental to secret sharing schemes, where a secret is divided among multiple parties using polynomial interpolation. Error correction codes also rely on polynomial division to detect and correct data transmission errors, ensuring secure and reliable communication. These applications demonstrate that polynomial division is not merely an abstract mathematical concept, but a critical tool that enables secure financial transactions, protects sensitive data transmission, and powers the cryptographic systems that secure our digital world. When faced with a polynomial division problem, you must choose between two primary methods: long division and synthetic division. The choice depends on the specific characteristics of your divisor polynomial. Synthetic division is specifically designed for linear divisors. It can only be used when your divisor is in the form x minus k, where k is a constant. This includes expressions like x minus 3, x plus 2, or any linear binomial. The main advantage of synthetic division is efficiency. It requires fewer steps, less writing, and reduces the chance of arithmetic errors. When applicable, it is significantly faster than long division. Long division, on the other hand, is the universal method for polynomial division. It works with any polynomial divisor, regardless of degree or complexity. Whether your divisor is quadratic, cubic, or contains multiple variables, long division can handle it. While long division takes more steps and requires more careful organization, it provides a complete and systematic approach that works in every situation. It is the more general method that every student should master. To help you choose the appropriate method, consider this decision process. First, examine your divisor polynomial carefully. Ask yourself, is your divisor linear, meaning it has degree 1? If the answer is yes, synthetic division is your best choice for efficiency and speed. If your divisor is not linear, or if it has degree 2 or higher, then long division is your only option. It will handle any polynomial division problem you encounter. Let me provide specific examples to illustrate this choice. Consider these divisor examples to see which method applies. For a divisor like x minus 3, which is clearly linear, synthetic division is the optimal choice. It will save you time and reduce computational errors. When faced with a quadratic divisor like x squared plus 2x plus 1, you must use long division. Synthetic division simply cannot handle polynomials of degree 2 or higher. Even when the linear divisor has a coefficient other than 1, such as 2x plus 5, synthetic division can still be used with a slight modification to account for the leading coefficient. In summary, the choice between methods is straightforward. Use synthetic division for linear divisors when efficiency matters, and use long division for all other cases, or when you need a method that works universally.